Right, so velocity time graphs. So let's have a little look at this. And remember, like previously, we were looking at distance time graphs. So don't get confused with the two. The essential difference is this is our velocity, our speed, just up here. So before I actually answer the question question is calculate the acceleration of the taxi 6 seconds into the journey, 10 seconds into the journey. Um, let's have a little look at what's actually happening here. Um, so we're gonna start from a standing start, and it's a constant acceleration until we get to 5 meters per second. What happens at that point is we don't stop. This doesn't mean we stop. It means we carry on at 5 meters per second, right, for another second actually. Right, so we don't stop here, and then we increase speed, or rather the taxi increases speed until we get to up here, which that's about, what's that, about 11, 12, about 12 seconds, 12 meters per second. Again, that's constant acceleration. And again, up here, it doesn't mean we stop, right? So on a distance time graph, this would mean that you would be stopping. We don't stop here. It means that we're carrying on at 12 meters per second. So actually the acceleration is zero during this period. It just means we're going at a constant speed and then decelerating here, right? So we're going to be getting slower but at a constant rate. So let's have a look at the questions. So calculate the acceleration of the taxi 6 seconds into the journey. So 6 seconds, so it means at this point just here. So we've already said during this period we're actually going at a constant speed. So the acceleration at that point is going to be 0. Now, we can also try and put the correct units in as well. Don't worry too much about this, meters per second squared, but just try and get used to writing that in, okay? And part B, so what's the acceleration 10 seconds into the journey? So here's 10. So in other words, what we want is we want the gradient of this line just here. The easiest way of doing that is to look at this as one section. Okay, we just got a triangle. We're just working out the gradients. All those kind of gradient skills just coming into play. Just want to work out the gradient. You can see the answer is going to be negative. So looking at this here, we're going to come down. So if we said that was, what's that going to be? That's 12, isn't it? Okay, so we've gone from 12 meters per second. So this line here is 12, and then we're going to divide by 1, 2, 3, 4. So although we got slower, so it'd be minus 12 over 4. So the answer is minus 3 meters per second squared. Remember, it's not speed. That's describing the acceleration. Or actually, we're slowing down, aren't we? Okay. Right. Let's have a look at a couple more ideas. Something else here, by the way. Let me just show you. Is that if you might get a curved line, and it asks you to describe, or rather calculate the acceleration at a particular point. Let's just imagine like 2 seconds into the journey was this point here, and the question's asking me to calculate the acceleration at this point. So all that would mean, now because this isn't a straight line here, I can't do it. Well, we can. So what we would do is we would put a tangent in at that point, and then we would work out the gradient of this line. Okay, so obviously that's a little bit more advanced. There's something else to look out for. So if I show you the next example, I'm actually going into that sort of idea. So it says, look at the velocity time graph for the tram on the right. Okay, so we've got a tram, so we've gone off, and it says, describe the velocity of the tram in the first second of the journey. So if I'm going to describe this, the velocity increases from 0 to 7.5. halfway between 5 and 10. Right, so it increases from 0 to 7.5 meters per second. That's all I would need to say. Now, describe the acceleration of the tram in the first second of the journey. So we start off really quick, the acceleration. Okay, so the acceleration is really quick, and then the acceleration slows. Doesn't mean the tram's slowing, it means the acceleration is slowing. Right? It's important to think of the difference between acceleration and velocity. Right? So if I'm looking at the acceleration here, the acceleration starts off really steep, and then when we get to this speed of 7.5 meters per second, then it just carries on at 7.5 meters per second. So then we can see the acceleration in here would be 0 for this part of the journey. Remember what I said, if you're asked to calculate the acceleration as well. Right, so if I was asked to calculate the acceleration at a particular point in the journey, now this bit's easy, this bit's relatively easy, it's a straight line. It's a straight line. Right? That's just a horizontal line, so therefore it's 0. That's easy. But if I was asked to do it in here somewhere, remember what I would do is that I would put a tangent in at a particular line. Now, I know this isn't the question here, but I'm just trying to emphasize this point. I'd put a tangent in at that point, and I'd work out the gradient of that. Now, obviously, that's going to change. Another way of thinking about it, look, the acceleration, really steep. Acceleration becoming less, okay? And then by the time we get up to the top here, you can imagine that line kind of turning around, and then it's going to be horizontal. Right, one more quick example to look at. Let's have a quick look at this one. There we go. So calculating distance from a velocity time graph. Now this is kind of like the main questions on this, they tend to be asking you to do this. Working out the distance on a distance time graph is easy. You can just read it off. Be careful if the journey comes back again, but should be kind of quite easy to do. The key point here is that the distance is the area in here. All right. Now I deliberately not put a question here. It just says this is the velocity of a runner. So he's gone off at a constant speed. A constant acceleration until he gets to 6 miles per hour. And then they run at a constant speed, that's the constant speed, and then they slow down at a constant rate. Now in reality it doesn't happen that way. We'd end up getting curves in there, okay? So if I want to work out the area, remember the area is the distance. Right? You need to link those two things together. Velocity time graph, the distance is the area. Now you quite often get a trapezium, so it's really useful to remember the area of a trapezium. And the area of a trapezium is the top bit, the bottom bit, and then we need to know the height just there. So if I want to work out the whole thing, it's just going to be, so the area of a trapezium, if I write that down first for you, is half of A plus B, and then multiplied by the height. Okay, if you think about it, it's just you're just averaging these two numbers just here, so you're kind of making it a bit like a rectangle. Right? A rectangle is just length times width, so it's a bit like that. So if I just go in, if we just go and sub in our numbers in here, so B is 2.5. We can see just there. I'm just putting in all the easy bits first, the things I can see without even thinking about them. And then we've got our height is 6, and then A actually is, it goes from 2, goes 1, it's actually 1.25. Remember, it's time, and time we need to actually put down as decimal. So now if I piece all this together, so 3.75, so I'm going to do half times 3.75, I'm going to multiply that answer by 6. So if we pop that into your calculator, and we're going to have, we've got 11.25, and we're talking about miles. Make sure we put the correct units in. Right. Now it might ask me to work out the average speed. Remember average speed? So that would be the distance over time. Again, another very common question to suddenly pop up. Obviously it's a little bit harder to do from here because you've got to really think about how to work out the distance. Right? So distance on the velocity time graph is the area. Sometimes if you've got a curved one, you might have to estimate. So you can just put a line in. All right. So imagine if this line here were curved. So in reality, it probably would be curved. So imagine if that was curved, just there. Whoops. If that was curved, then we would just connect a straight line, and we would be underestimating the distance just very, very slightly. But quite often, you'll get like a curve there, and then maybe the curve go the other way. So they kind of balance each other out. Okay, something to look for. Right then. So let's try and do a few questions and see how we get on.